Other teaching and learning models in the research that are inquiry-based and constructivist models can be embedded into the larger learning cycle model. 3 of these models include the PEOE model, the generative learning model, and the conceptual change model. I will now involve you in a learning cycle called Sticking Together. As I go through this learning cycle, I'll be sometimes modeling, that is, speaking to you as I would a classroom of students, probably grades 4 to 8. And you might recognize the ways the same learning cycle could be used for younger students as well. I'll also take off my teacher hat periodically and put on my professor hat to give you special teacher tips and to point out the reasoning behind some of the steps in this learning cycle. Before continuing the video, gather the materials listed on the slide so that you will be able to participate in the activities as I give instructions. That will help you prepare for actually using this activity in your own classroom. For the exploration phase, you need to have the following materials, and when doing this with your students, have the designated materials collector of each group pick up a bin prepared with the following items: an eyedropper, which can be purchased at a drugstore, a penny, a clear plastic cup, small one, and a couple of large ones. Then you will need food coloring, you'll need some wax paper, plastic spoon, and then what you're going to do is either ask the children to fill the cup with water, or I usually do this ahead of time for them. I also sometimes have a pitcher of water on the table so they don't have to get up out of their seat, plus paper towels on the table as well. Then post the given chart on the board or overhead. Now you are to participate yourselves. Be sure you've gathered the materials and have them in front of you. We'll start with Exploration A. Before beginning this activity, make a prediction. Predict how many drops of water you think will fit on the head side of a penny. Write that prediction on your paper under Predict. Under Explain, write an explanation for your prediction. That is, answer why you think the number of drops you predicted is correct. Now at this point, I ask the students to tell me their prediction and I write them down. Now I don't ask for their explanations yet. Before the predictions, the students typically offer numbers such as 5 drops will fit on the head of the penny, or 2, or maybe 10. How many did you predict? Now you try it. Drop as many drops of water on the head of a penny that can fit before the water is full and spills off. Write that number on your table under Observe. How many drops did you observe fit on the head side of a penny? Try it more than once if you would like. Okay, now from the professor's perspective, I write on the chart the numbers of drops that actually fit on the penny as reported by the children in class. I ask the children to look at the numbers and tell me what they noticed between the numbers on the predicted chart compared to the observed chart. For mathematics integration, I would ask the children to calculate the average predicted and the average observed. The children noticed, and we discussed, that the number of drops predicted was less than the number of drops we observed actually fit on the penny. On the chart under the second Explain, write an explanation for your observation. I also asked children their explanation before the experiment and after. Before the experiment, the children often responded with statements such as, I predict 3 drops will fit because the penny is small and the drops won't fit. The explanations after they placed the drop on the penny and found out that so many more drops actually fit on the head side are that the water clumped together, or the water made a bubble, and more was able to be added to that bubble, or that the water sticks together. Then we move on to Part B of the exploration phase. You do this part as well. Drop some food coloring in a glass of water just to make the water more visible, and stir. Now take your eyedropper and place a few drops of water on the wax paper, but in different locations on the paper. Just spread it around so the drops aren't touching one another. Okay, now holding this wax paper tight, roll the water on top around and observe what happens. Careful not to spill it off the edge. But now allow the separate drops of water to touch one another. What does the water do? The students say that the water clumps together. They say that the one water droplet, when it touches another, sticks to another one, so that water sticks together. The concept, invention, explain phase then follows, where I ask students to review what the water did in parts A and B of the exploration and to make a statement that describes their observations. You write a statement now. What did you write? The children typically construct something like the following statement: water sticks together. Now for the term introduction. What you just described is a property of water called cohesion. Now we move on to application. Many different directions can be taken for the application or elaboration phase. One application is to have the students place the drops of water on the head of the penny again until it's full, to the point where it is about to spill off. With the water in that bubble shape, and with your index finger, gently touch the top of the bubble and then lift up. What do you observe? Students say that the water bubble springs back. We talk about cohesion of water on the surface of water being stronger because the surface is two-dimensional rather than three-dimensional as it is below the surface. If students are advanced, we discuss the polar nature of the water molecule. That is, that water has a negative end and a positive end like a magnet. We can draw or go to a website to look at models of the water molecule. Because each water molecule is polar with a negative end and a positive end, one water molecule's positive end is attracted to another water molecule's negative end. The attraction is called hydrogen bonding. It is not an exchange or sharing of electron as with other type of bonds. It's only an attraction, analogous to the force between the opposing ends of two magnets. The arrangement of those water molecules is more organized, and each molecule is aligned with another on the surface more strongly, whereas below the surface the water molecules are more free to move around and align in different ways. I'm sure you've heard this phrase before, but what this is called, this tighter attraction between the water molecules on the surface, is surface tension. Now we discuss other ways we may have experienced surface tension, such as doing a poor dive off the diving board and splatting on our stomachs. Do you remember how much that hurt? Why did it hurt? It's because of surface tension. We also discuss water insects and why they can scoot across the surface of the water without sinking. This is because the special kind of water cohesion that's on the surface, where the water molecules are aligned more tightly together, and this is called surface tension. For another application, you'll need dish soap, your penny, water, and the eyedropper. For this one, we play with surface tension. Make sure you have or that you remake the bubble or dome of water on your penny, as many drops as you can fit on it. Now you need to get some dish soap and put a drop of dish soap on your finger. Now gently touch the surface of the bubble with your soapy finger. What happened? And why did that happen? Yes, what children find is that the soap broke the surface tension. The molecules of soap got in between the molecules of water and separated them such that the water couldn't stick together anymore. So it broke the surface tension. As another application, we do the following. You need a clear glass or plastic cup of water and either some baby powder or some pepper. Sprinkle the surface with the pepper or baby powder and observe what happens. What students notice is that the pepper stays on top. Why does it stay on top is the question, and of course that's because of surface tension. Now you take the soap and you put a drop right in the middle of the surface of the water and observe what happens. What students observe is that the surface tension was broken and the pepper immediately drops down to the bottom of the glass. It spreads it out and drops it down. So it sinks in the cup. So again, the soap gets in between the water molecules, the hydrogen bonds that I just explained, and separates the water from each other. So now there's room for the pepper to fall through. Other applications involve extending the concept of cohesion to another related concept. Here you'll need a cup of water with food coloring. You can use the same one that you use in the exploration. A celery stalk and paper towel. Place the celery stalk in the water and leave it there for several hours overnight. What do the children observe? The way to find out is to break the celery stalk in half and look at the broken end. What they'll see is that the food coloring moved up through the tubes inside of the celery stalk. And now you ask, why did this happen? Now dip the corner of a paper towel in the colored water and observe what happens. The students notice that the water goes up against gravity into the paper towel. Why did this happen? The related concept for both of these activities is that not only does water stick together in cohesion, but water also sticks to other things. It's attracted to other objects, such as the paper towel or the walls of the tubes inside the celery stalk. This property of water is called adhesion. Adhesion is very important because if water did not stick to your skin or to the floor, for example, we could not wash. The water, being like a magnet, is attracted to the dust and dirt and washes it away. In the case of celery, adhesion is important as well as cohesion. In order for the water to move upwards in the plant against gravity in one continuous chain, the water has to be attracted to another water molecule in cohesion, and it has to be attracted to the walls of the vessels inside of the celery, or all plants for that matter, because of adhesion. That is the movement of water, and the movement of water in small spaces or tubes against gravity is called capillary action. Now, what other applications can you think of, particularly as ways to integrate across the curriculum? Would you have children pretend, for example, that they're a water molecule and write a story about their adventures? What else? Now you think of others.